So the first couple of units we saw this year covered polynomial functions and rational functions. And so what I'm going to do first is I want to just highlight the lessons that I'm going to kind of focus on in this video, and then go through a couple of notes on polynomial functions first. So first, this video is going to focus on problems and concepts from lesson 2.06, available in the OneNote, as well as lesson 2.08, which is also in the OneNote. So let's start with polynomial functions, and these two lessons cover factoring trinomials, and graphing polynomials. Okay, so we're not going to review all of the concepts from Unit 2, but these are the two I want to focus on. I think these are the most important. These are the ones that you're going to see aligned to the final exam. To factor, or I'll say factoring, a quadratic function of the form. Okay, let's say I have a times x squared plus b times x plus c. Okay, so let's say we have this is called a trinomial because there's three terms. More specifically, it's a trinomial that has an a value that's not equal to 1, which means the factoring is a little bit more complicated. So in order to factor this, you need to find two numbers. And we'll go through an example of what this looks like in a second, or in the first problem set. So find two numbers that multiply. To the product of the a value and the c value, and add to the b value. So two numbers that add to a times c, but also add to the letter b. Once you do that, you're going to use these numbers to split up the x terms. The x term, I'll say, meaning the linear term of the trinomial. So in that case, this would be, or in this case, this would be the b times x. All right, then once you do that, we're going to use grouping to factor. Okay, and like I said before, I'm going to go through an example of this in a second once we go through the first problem set. Okay, so that's kind of the first thing you need to know. I think this is the most important thing from Unit 2. Now, covering Unit 3, the lessons, we're going to focus on our lesson, or I should say the lessons that the problems are aligned to are lesson 3.06 and lesson 3.11. These cover rational operations, as well as graphing rationals. Okay, so in this video, what we're going to do is we're going to cover two problem sets. One is going to approach these concepts from polynomial functions and rational functions from the algebraic perspective. And then the second problem set is going to approach it from the graphical perspective. So the first set of problems are going to be algebraic. The second set of problems are going to be graphical. Okay, so let's start with problem set 1. So to start problem set 1 off, we're going to go through some operations with rational expressions. I'm going to go through a division and subtraction question division is very similar to multiplication, and then subtraction is very similar to addition, if you guys remember from Unit 3. So when we're dividing two rational expressions, the first thing we want to do is we're going to keep the first expression the same, but what we want to do is multiply by the reciprocal of the second expression. So instead of 5x minus 5 over x plus 5, let's change it to x plus 5 over 5x minus 5. And notice we've changed the sign here from a division sign to a multiplication sign. So what we could do here is we're going to multiply across, but what we could do is distribute all of these terms, try to simplify it. What's going to be a little bit easier to do is factor all the terms that we can to try and cancel some things out and make the expression easier to work with when we're doing the multiplication. So what I'm going to do here is factor each term. So x squared minus 6x plus 5. You guys should know how to factor this. X minus 1 times x minus 5 over x squared plus 6x plus 5. It's going to be x plus 5, x plus 1. And we're going to multiply this by x plus 5 over, and we can factor a 5 out of the denominator of the second term, 5 times x minus 1. So what will happen now is the x plus 5s will cancel. The x minus 1s will also cancel. And so we're left with x minus 5 over 5 times x plus 1. But the question wants our final answer to be in standard form. And so what that means is we're just going to multiply the 5 in the denominator to the x and the 1. So our final answer here for the first one is x minus 5 over 5x plus 5. Okay. So the next one is the addition and subtraction are a little bit more complicated just because there tend to be a little bit more steps. So what we're going to do here is we're going to change the expression so that they're factored again. So I'm going to factor an x out of the denominator of the first term, and I'm going to factor a 4 out of the denominator of the second term, giving us the following. In order for us to be able to make this subtraction, the denominators of both of these terms have to be the same values. To do that, what we're going to do is multiply the first term by an expression that is equivalent to 1, and that is going to be 4 over 4. So 4 times x plus 8 over 4 times x minus 8 minus. This one we're going to multiply by x over x. So x times x minus 8 over 4 times x minus 8. Okay? So now we have two expressions that are that have the same denominator, so we can multiply these together. So 4 times x plus 8 minus x times x minus 8 all over 4 times x minus 8. Okay. And the last thing we're going to do is we're going to convert this to standard form. So what we're going to do is distribute the numerators here. I'll do this over here. So 4x plus 32 minus x squared plus 8x all over 4x squared minus 32x. And then to get our final answer, let's just combine like terms in the numerator. Negative x squared plus 12x plus 32 over our denominator. Okay, and here's our final answer for number 1, letter B. What we also need to be able to do is solve rational equations. So we're just dealing with rational expressions. Now let's deal with a rational equation. So if we have the following equation here, the trick behind solving a rational equation is we're going to look at the denominators. And in this case, because the terms both x, or in this case b plus 2 and b minus 2, are both they're both factors of this last term, there's kind of a trick we can use here. And that trick is to multiply everything by b squared minus 4. Okay? So we're going to multiply the left-hand side by b squared minus 4 and the right-hand side by b squared minus 4. And so what that would look like is b squared minus 4 over b plus 2 times b squared minus 4 over b minus 2 equals b minus 2 times b squared minus 4 over b squared minus 4. So it looks pretty messy, but this will simplify. And the way it's going to simplify is the following. B squared minus 4 can be factored to b plus 2 times b minus 2. It's a differences of squares. And so if we have b plus 2 times b minus 2 divided by b plus 2, this actually just becomes b minus 2. The second term will become plus 2 times b plus 2 equals what's left after we cancel these out. So now we're left with a linear equation. So b minus 2 plus 2b plus 4 equals b minus 2. This becomes 3b plus 2 equals b minus 2. Let's bring the b over and the 2 over, so 2b equals negative 4. And so we get b equals negative 2. So, is that the answer? It is actually not the answer in this case. And the reason why it's not the answer, because if we were to take this here, b equals negative 2, and plug it into this equation, we're going to get an undefined value in both the first term and this last term over here. Because if you plug in b equals negative 2, we're dividing by the number 0, and you cannot divide by the number 0. You get an undefined output. And so we say this is an extraneous solution because the equation is undefined at b equals 2. Negative 2. So the solution here is that there's no solution. So in other words, there is one value of b that makes this equation true, and that value is b equals negative 2. However, the equation is not defined at that b value, and so we cannot say that that's a solution. We have to say there's no solution. All right, and we're going to wrap up this video, excuse me, by going through just some polynomial review. So what we want to do here is factor this, and this goes into the notes that we took earlier in this video. So basically what we want here is we want two numbers that multiply to the product of the a and c term. That's going to be negative 60. And two numbers that add to negative 7. So you might have to do a little bit of trial and error for some of these, but in this case it's negative 12 and positive 5. And so what we can do here is we can rewrite this trinomial as 6a squared minus 12a plus 5a minus 10. And then we can do a little bit of factoring by grouping. So I can factor as 6a out of the first two terms, and I can factor the number 5 out of the third and the fourth term. Once we do that, we can actually factor these out from these two terms. So we have 6a plus 5 times a minus 2. And that is the answer for number 3, letter A. Okay, letter B wants us to find a minus 6x, sorry, 8 minus 6x minus 9x squared. To make this a little bit easier, I'm going to factor out a negative 1 from each term. And now let's see if we can do factoring by grouping here. So we want two numbers that multiply to the product of 9 and negative 8. That's negative 72. And add to positive 6. Okay, so take a moment to think about what those might be. They are 12 and 6. And so we get negative 9x squared plus 12x so it should be negative 6. So plus 12x minus 6x minus 8. Okay, now let's factor a 3x, least common factor, between the 9x squared and the 12x. So 3x times 3x plus 4 minus, let's factor a 2 times 3x minus 4. Okay, we have the same terms here, so the factoring by grouping is going to work. So our answer is going to be negative 3x minus 2 times 3x plus 4. That's the answer for this one. Okay, now let's work through problem set number 2. Okay, problem set 2. Our goal in this problem set is we're going to approach polynomial functions and rational functions through a graphical lens. So we're going to try and graph these. So starting off with number 1, we're going to start with g of x, and we've defined g of x as this cubic function here. So our goal here is to graph this. The first thing we want to do when we have a polynomial function is, if we can, let's see if we can factor this. So let's do a little bit of factoring by grouping. I'm going to factor an x squared out of the first two terms. And then I'm going to factor a 25, or a negative 25, out of the third and the fourth term. The factoring by grouping works here because these two terms are the same like they were in the last problem. So we have x squared minus 25 times x plus 1. Now we can factor the x squared minus 25 because that's the differences of squares to x plus 5 times x minus 5 times x plus 1. And this is g of x. And the reason why we want to factor this is because if we factor it, the usefulness of having a polynomial factors is it's easy to identify the x-intercepts. So the x-intercepts here are going to be the values of x that cause this whole term to become 0. Okay, and there's 3 of them here. The first one, as a coordinate point, is negative 5 comma 0. That comes from this term. The second one is 5 comma 0. That comes from this term. If we plug 5 into the middle term, it becomes 0, which makes the entire function become 0. And then the last one is going to be negative 1 comma 0. So those are the 3 x-intercepts. Let me draw a coordinate plane over here that have those values located at the x-axis. So negative 5 comma 0, negative 1 comma 0, and then 5 comma 0. This is not going to be perfect, but as long as it's somewhat accurate, that's what we're looking for. Okay, the y-intercepts. There's only going to be one of them. That is going to be determined by the y value, or the value of the function when x is equal to 0. If we have a polynomial function, all of the terms are going to have an x in them except this term, if it's there. And so if we plug in 0, everything becomes 0 except the negative 25. So the y-intercept here is 0, negative 25. So again, not drawn to scale, but it'll look something like that. Okay, now if we want to graph this, remember if it's a cubic function, it kind of has that S look to it, where the endpoints point in opposite directions, because the degree of the function is odd. So it'll look something like this. It goes up, comes back down, and then go up. I don't think I ran through that last point. Let's try that one more time. Goes up, comes back down, and then it goes through that last point. And that's all I'm looking for a question like this. We could identify like this point or this point down here if we really wanted to, but as long as you have the x-intercepts and the y-intercept, that's kind of what I'm just looking for this one. Okay, to wrap up this video, let's do the same thing, but let's do it with a rational function. So f of x is equal to x plus 1 over x minus 3. So graphing a rational function. The first thing we want to identify is the horizontal asymptote. The horizontal asymptote can be identified by using that acronym BOBA and eats DC. The exponents are the same here, so we're going to divide the coefficients. And so the horizontal asymptote is equal to 1. The vertical asymptote is the x value that causes the denominator to equal to 0. So think about what x value I'd have to plug in here to get the denominator equal to 0. Well, that x value is going to be equal to 3. So on our coordinate plane, let's start this question by identifying the horizontal line, y equals 1. So let's just draw a horizontal line here. And let's draw a vertical line at 3. So like, let's say here, y equals 3. Okay, we also need to find the x-intercept and the y-intercepts. The y-intercept can be found by taking the function and plugging in 0 for x. So y is equal to 0 plus 1 over 0 minus 3. And so the y-intercept is negative 1/3. As a coordinate point, it would look like this. And so that is right. Let's say it's right here. And the x-intercept can be found by setting the function equal to 0. So 0 equals x plus 1 over x minus 3. In order to solve this, the way you can think about this is we can multiply by x minus 3. And so we end up with just 0 is equal to x plus 1. And so the x value of the x-intercept is negative 1, which means the coordinate point of the x-intercept is negative 1, 0. Okay, and that's going to be like, let's say right here. Okay, so this is 0, negative 1/3. This over here is negative 1, 0. The last thing we're going to do is we're going to pick a point that is to the right of the vertical asymptote to identify the behavior of the graph over in this region right here. So we want to figure out what's going on over here. To do that, we're just going to pick a point that's to the right of the vertical asymptote. The vertical asymptote is located at x equals 3. So let's pick a point that's larger than x equals 3. Let's pick x equals 4. So I'm going to plug 4 in for x into this function. So we end up with 5 over 1, or 5. So we have the coordinate point 4, 5. And let me locate that here. So 4 is about right here. I'm going to go up 5. Let's say it's like right here. Okay. Last thing we're going to do here is let's graph this. So we know that the function will approach the two dotted lines asymptotically, which means that they're going to get closer and closer and closer to, but never cross or touch. So the left-hand side will look like this. Starts over here, comes down, runs through these 2 points, and then goes, let me do it one more time, then goes down forever. These 2 points, and then it will cross down. Similarly, to the right, it's going to be over here, comes down like this. Okay, and that's the graph of the rational function, x plus 1 over x minus 3. There are the following steps: horizontal asymptote, vertical asymptote, y-intercepts, x-intercepts, additional coordinate point to understand the behavior on the other side of the vertical asymptote. Okay, that is it for the video today. To wrap up class, I want you guys to go through the additional practice, which is going to involve some more challenging questions that we saw earlier this year.